Welcome back to The Deep Dive. Today we're taking you inside a regulatory process that is about to fundamentally change the U.S. domestic medical supply chain.
It's a huge deal, a really huge deal. We're talking about the final step in a multi-year effort.
Right. This is the culmination of the Nuclear Regulatory Commission's, their comprehensive review for the operating license of Shine Technologies' massive facility in Janesville, Wisconsin.
And that clearance is just monumental. For those of you who track this space, the U.S. has been so reliant on imported medical isotopes.
Specifically molybdenum 99, Mo-99.
Exactly, and often sourced from these old reactors using highly enriched uranium, HEU. But the NRC staff has now determined that Shine's facility, its design, its operational criteria, it's all acceptable.
And crucially, the Advisory Committee on Reactor Safeguards agreed. They recommended the operating license be issued, so the green light is on.
It is. This facility is the path forward for a reliable HEU-free domestic supply of Mo-99.
Which is vital for millions of medical procedures every year. So our job today is to look past the headlines, get into the NRC documents, and unpack the most critical engineering, operational, and financial assurances that got this project over the line.
We're really drilling into the risk mitigation. The details that make sure this thing can run safely for the next 3 decades.
That's the key. 30 years of reliable supply.
Okay, let's unpack this. Let's start with the core technology.
All right, so let's start with how Shine's process is different. Mo-99, the isotope they need, it's a byproduct of nuclear fission. Legacy systems use solid fuel plates.
Okay.
Shine uses a low-enriched uranyl sulfate solution. So think liquid fuel. The fission happens right there in the liquid.
A liquid fuel setup. That sounds revolutionary for this sector, but also incredibly complex. How do they actually start the reaction in that solution?
They use an accelerator. They bombard tritium with deuterium, which fuses and creates this huge pulse of neutrons.
And those neutrons are what drive the fission. That's it. Those neutrons hit the uranium solution, and you get fission, releasing the Mo-99. They're creating the neutron flux they need without a traditional sustained reactor core.
And the facility itself is split into different zones, which I imagine has to do with handling these radioactive liquids.
It does. The whole place is broken into 2 main parts. First is the irradiation facility, or IF. That's where the fission happens.
Okay.
The second, and this is probably the most complex part, is the radioisotope production facility, the RPF. This is where they take that hot liquid, process it, and pull out the pure Mo-99 for shipping. And the license covers both for 30 years.
Right. You can see the risk management just in separating those functions. But I also saw they're doing a phased startup. It's not like they're just flipping one giant switch.
That's right. And the NRC really looked at this phased rollout. The plan is to bring their irradiation units, IUs 1 through 8, online one by one.
And the NRC was okay with that.
They confirmed that the modular design is robust. Each IU operates independently. So an issue with, say, Unit 7 doesn't affect the safety or operation of the first 6.
So the modularity itself reduces the execution risk during that ramp-up phase. You're not betting on them hitting 100% on day 1. They can build up and learn as they go.
Exactly. It de-risks the whole thing, both financially and from a regulatory standpoint.
Okay, so once the NRC was comfortable with the internal chemistry and the startup plan, they had to look outward. At the site itself, Janesville, Wisconsin, described as flat farmland. But the review of external hazards was incredibly detailed.
Oh, it was a deep dive into probabilities.
Yeah.
What's really fascinating is how regulatory science translates these, low probability events into hard engineering requirements. They look at U.S. Highway 51, which is just 0.22 miles away.
Why does a highway less than a quarter mile away trigger that kind of analysis?
Because of what's on that highway. The potential for a catastrophic accident with, say, highly flammable materials. The NRC needed absolute proof that a worst-case scenario wouldn't compromise the facility.
So give us the takeaway from that. What did they model and what was the result?
Well, they modeled a full 50,000-pound propane truck rupturing, a BLEV, a boiling liquid expanding vapor explosion. It creates an insane but very short fireball.
In the building.
The analysis showed the concrete structure could just absorb it. That massive instant heat shock barely even registered on the inside. The temperature rise was insignificant.
So high heat, but so fast it didn't matter. What about a longer burning fire?
You modeled that too, a big gasoline tanker pool fire. Lower heat, but it'll last for about a minute. And again, the facility's design proved resilient. The review concluded no adverse impact on safety.
That is an impressive level of rigor. And I know they're near the Southern Wisconsin Regional Airport, so I'm guessing aircraft impact was also on the list.
Absolutely. They had to pick a design basis aircraft. They chose a Challenger 605 and model a direct impact. They had to prove the structure would hold, that the critical containment areas wouldn't be breached.
So whether the threat comes from the road or the air, the physical shell is ready for something pretty massive and pretty improbable.
Which brings us inside to the most complex part of the operation, managing the safety of this aqueous solution.
Right, and that raises a huge question. How do you manage nuclear criticality safety when your fuel is a liquid, something you're constantly moving and concentrating? It seems way more complex than solid fuel rods.
It is more complex. You don't have that fixed geometry. So criticality safety is everything, especially in the RPF, where they're concentrating the uranium solution. The solution itself is low enriched, just under 20% U-235.
And what's the safety philosophy for that liquid?
It's a very strict hierarchy of controls. It's a key NRC concept. Think of it like a pyramid of safety barriers. They have to rely on passive engineered controls first.
Passive controls. What's an example of that?
It means the system is safe without anyone doing anything, without any power. For criticality, that means using geometrically safe tanks. The tanks are physically shaped so that no matter how much liquid you pour in, it can never ever reach a critical mass.
That makes so much sense. The shape itself is the safety feature.
Exactly. Inherently safe. If that's not possible, then you go to active engineered controls, pumps, valves, interlocks, and only as a last resort do you use administrative controls, human procedures and training.
So the goal is to design out human error, but there has to be a number, a safety buffer they measure against.
There is. The required margin of subcriticality is set at greater than or equal to 0.06. For those of us who aren't nuclear engineers, what that number really means is there is a substantial buffer. It guarantees the system is safely far away from criticality under all credible conditions. It's very conservative.
Okay, beyond criticality, you have the byproducts. In a water-based solution, you're going to get hydrogen gas from radiolysis. That's a huge explosion risk.
The classic chemical engineering problem in these systems, yeah? Radiolysis breaks down the water, you get hydrogen. During normal operations, they have the target solution off-gas system, or TOGS. It's actively monitoring and managing the hydrogen, using blowers and recombiners to keep it way below the flammability limit.
But what about a total power failure? What if TOGS goes down?
And that is where the real redundancy, the real supply chain assurance is born. The backup is the nitrogen purge system, the N2PS.
Okay.
It uses huge pressurized tanks of nitrogen to just sweep the hydrogen out. It's entirely passive, it uses stored pressure, and it keeps the hydrogen level safe.
How long can that passive system run for?
Up to 3 full days, with no external power, no human intervention. And that's the real insight for the market here. A 3-day blackout won't stop them. That's a massive assurance of reliability.
An incredible safety cushion. Now let's talk about the digital brain managing all this. The level of digital safety they engineered is...
Well, it's fascinating.
It really is. The reactor protection system, the engineered safety features, all the critical safety functions run on a single platform, the highly integrated protection system.
But with any digital system, the nightmare scenario is a common cause failure. One bug takes down your redundant systems at the same time.
The one flaw that beats everything. So how do you prevent that?
How do you? Diversity. Yeah. This is digital defense in depth, taken to the absolute extreme. The design uses 3. Fundamentally different. Field programmable gate array technologies. FPGAs.
Right, FPGAs. So these are like configurable microchips.
That's it. They execute the safety logics. And by using 3 totally different chip architectures with different development tools, maybe even different software languages, they make sure a single flaw in one can't possibly affect the others.
Wow. So even if there's some global cybersecurity flaw or a design error that hits 99% of digital controls out there, this facility's core safety brain is isolated and functional. That has to be a huge reason the NRC is okay with a 30-year license.
Absolutely. Now, beyond the engineering, the NRC has to look at the people and the processes, the administrative readiness.
Right. Licensing isn't just about the hardware.
Exactly. Licensed operators, for example, have to go through this continuing training program that pulls requirements from both power reactors and research reactors. It's a hybrid, and it's an exceptionally high bar.
I also saw a really interesting safety trade-off they made with fire protection. They're not using automatic sprinklers in the radiologically controlled area. That seems backward.
It's a true safety paradox, and it shows you the unique challenges here. While sprinklers fight fires, adding water into that area creates 2 much bigger hazards. The first is nuclear.
How so?
The water could act as an unexpected moderator for the neutrons, and it could actually accelerate the fission process. you could risk a criticality event.
So putting out a fire could start an uncontrolled nuclear reaction.
Precisely. And the second risk is that the water would spread radioactive contamination everywhere. So instead, they rely on an automatic fire detection system. They chose to mitigate the nuclear risks over simple property protection. It's consistent with building code exemptions for these kinds of special hazards.
That choice really tells you how seriously they take the risks of liquid fuel. Okay, finally, let's touch on the corporate side. Financial qualifications and foreign ownership, control, or domination, FOCD.
Yeah, the NRC has to make sure a foreign entity can't control the facility. It's a national security issue. They looked at Shine's structure, a single-member Delaware LLC. They did note that one person on the board of directors is a Canadian citizen.
And how did that get resolved?
The staff did a deep dive on the corporate governance and determined that that one single member cannot exercise effective control over the company. So they found no evidence of FOCD, clearing another key hurdle.
So the legal and ownership path is clear for domestic operation. Okay, so to recap, we've seen just this extraordinary detail required for approval. From, calculating a highway propane explosion to designing triple redundant digital control systems.
This level of rigor is really the proof. It shows that the engineering pathway for this new HEU-free domestic supply chain is fundamentally sound and robustly protected against, well, pretty much everything.
So what does this all mean for you, the learner? The NRC's final word is that they are confident the design provides adequate protection, that the 30-year operational life won't endanger public health or safety. This green light massively de-risks a huge piece of the U.S. medical supply chain.
Which brings us to our required disclaimer.
This is not financial advice.
But the major regulatory hurdle is now cleared, and that reduces future uncertainty for Shine in a big way.
So the outrageous but plausible trade.
Okay, you short the domestic distributors and competitors still stuck on imports and the old high-enriched uranium tech. At the same time, you go long on specialty non-nuclear engineering contractors right there in Wisconsin.
The outrageous part of that is betting on a perfect, seamless, and accelerated ramp-up.
You're betting all 8 of those irradiation units come online faster than anyone thinks, driven by a new, motivated workforce, and that it causes this immediate structural shift that just tanks the old players before the analysts even see it coming.
But the plausible element is that the NRC documentation confirms the path is clear. The biggest regulatory risk is just gone.
Now here is a provocative thought for you to think about. Considering the incredible, rigorous analyses they did on external hazards, a truck fireball, an aircraft impact, what unexpected, low-probability, internal operational risk might be the largest financial threat to their startup schedule now?
Okay.
Think specifically about the specialized crane systems they have to use inside the facility, the ones for handling heavy, highly radioactive components during maintenance and refueling. What happens if one of those fails?
Something to think about as Shine moves from building to operating and starts lifting those very heavy, very hot pieces. Thank you for joining us for the deep dive.